To get some motion in the game, we will need to add our dynamic entity, something that has velocity and can move around. So create a new class, pour yourself a cup of coffee, let's get this done. We'll name it dynamic entity, it inherits from static entity, and we can press Alt Enter to create the constructor, and then we can generate some overrides, and what it needs is update and on collision. The thing dynamic entity cares about, of course, is motion. For motion, we need velocities, and at the moment, velocity is in the entity base class. It doesn't need to be here, because nothing, like the direct child class of entity is a static entity, and it can't move. So we can move this into dynamic entity, which is the first place in this hierarchy where velocity becomes a factor. We don't need to update the superclass because nothing happens there. So the naive thing we want to do in this class is basically integrate velocity to our position, just like before, but this time scale it with time. dt is delta time. It's the time since last time we updated, and it's a fraction of a second. Let me see, that's a double, that's a float, this is a float. Why is it not complaining about types here? Well, it really should. This should need to be cast. We'll see if it complains when the compiler looks at it in a bit. Do the same for y, but more useful, I think, is to integrate some gravity here. The velocities, of course, needs to be set somewhere, and right now they're set nowhere. We will probably add something like a target velocity or a target speed that can be used by our controller classes later on when we make the player, which will have access to controllers. And so maybe actually just do the gravity here. Whatever these values are right now, nothing will happen because the delta time is 0, so we will multiply by 0 and thus add nothing, and the thing will just be static. So we can start with going to the level manager and fixing create entity. Where we're creating the player, let's just change that out for a dynamic entity so that we can see it spawn. We'll change it for the proper class later when we have it done. So let's start here. Nothing. There we go. We have the player entity. It's scaled correctly. It's positioned correctly. Obviously not moving. So let's add a gravitational acceleration here. Actually, let's just call it gravity, whatever. And I have no idea what this value should be because I'm going to scale it every frame, and so I'm just going to call this 40 meters per something, probably 40 meters per second. And this is a setting. I'm going to make the actual gravitational acceleration of our entity a member. A lot of your dynamic entity you will not want to have falling. Something you notice when you start building games is simply you need to be able to turn gravity on and off on a per instance basis. So I'm going to make this a float member. I make that public too in case we want to turn it off from somewhere else. Let's just call that gravity and set it to that value. And so what I want to do at this point is something like, let's calculate a gravity this tick. So that's our, I should probably be casting that as well. Gravity times delta time. That's how much I want to add every frame to our velocity. So velocity y plus equals gravity this tick. And I'm just naming this to keep it clear what's going on here. We might not want this temporary here. It probably doesn't matter much anyway. So our velocity will always grow because of gravity, and then we will increment our position with that velocity. One problem here is that it will grow infinitely, and that will lead to a problem with tunneling. Right now we don't have any collision detection, but when we do, we will sample once per frame. And so if our entity is moving, let's say that this wall, right, is 1 meter wide, because it is 1 meter wide. If our entity is moving 2 meters per frame, i.e. per tick, it might be on one side in one update and not collide, and the next update it will be on the other side and still not collide. We will have tunneled through. So we want to make sure that we limit the maximum amount that we can move in one update to something less than half of the smallest entity we care about. So in my case, I might want to set a maximum amount of displacement to 48 centimeters per tick. So this is not a metric measurement, this is an actual pixel value, just to make sure we don't... it is a metric measurement, but it's not scaled by time. So it's the maximum distance we can move in a single update step. I'm going to just lock that in now. Private static final float, and let's call that max delta, and it's going to be the same on both axes. And in this case, I'm actually going to do 48 centimeters because, again, these blocks are 1 meter wide, 1 meter tall. If I did 50 centimeters, I could tunnel in one step. I could end up in the exact center. And then when our collision resolution steps in, we will implement that in the next video, I will be ejected to either side. I want to make sure that if I penetrate, I can only penetrate just shy of halfway, and that way I will be ejected on the correct side. And of course the user don't see that because we only render once per frame as well, so all collision resolution will happen before we draw the frame, and so that will look robust. To make sure that we never grow, or rather add more than we should, we can clamp this value. So this is the final value that gets added to our position. We need to make sure that it is clamped. And that needs a float, which means a lot of parentheses here, because I'm working with a double. And we need to clamp it to max delta in either direction. So we can't move faster than negative max delta or positive max delta. Told you the clamp would become useful. I'm going to do that on X as well. So now we have gravity and we have an X velocity being integrated. This is without any collision whatsoever. And again, nothing will move because we don't have the time. So let's do the time now. While this builds. Yeah, there we are. So, delta time. We are going to need a conversion factor. The system can provide us with time in nanosecond precision. This is crazy, but for some reason the Android platform, most of the mobile systems, have a very efficient way of getting high resolution clock. So if you call system nanotime, save that in a long, this is simply the time since the system booted or the time since your application started. I'm not entirely sure. It doesn't matter either. Come on, give me the value, blah, blah. Right, so since the virtual machine started. Doesn't matter. It's since a time ago, and that's all we care about, relative time that has passed. I'm going to create a conversion factor because nanoseconds is way too small for us to work with. We want to convert it to seconds. So nanoseconds obviously is going to be very small parts of a second. We will have fractions. We do private static final float. Let's actually make that a double because I want to work with doubles. And I want to convert nanos to seconds. And that conversion is 1 second divided by, let's see, 1. And now for nanoseconds, that's 9 zeros. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Let's double check that. 1, 2, 3, 1, 2, 3, 1, 2, 3. That should be the appropriate conversion ratio. So I create the last frame variable before I start the loop. Every time we start a new tick, we need to update this. Let me write this code out and then you'll see. So first we can calculate the delta time here. We do a final float delta time equals current clock. So system nanotime minus the last frame time, i.e. when the last frame started. and then we scale that to seconds. And this is bad because reasons. That should be a double. I keep writing floats out of habit. And so, yeah, current time minus the last time we started a frame gives us the amount of time that passed since that last frame. And as soon as we've calculated that, we can update last frame to make sure that that's accurate. So we do last frame, then we do all the work. And so when we come back up here, this value will of course be older. And then we simply pass DeltaTime into the update. Let's see, that should be good, I think. We build and see if the thing updates. It probably just falls out of screen at the moment, which is fine. While that builds, I can check. It's 10 minutes. Okay, so sorry, I ruined that for you. She did indeed fall off screen. We can fix that easily. Yeah, there we go. So let me see, in utils, I haven't brought those in yet. If you go to the course website, there is a thing for random number generation, just a few utilities that you can take, something that we could write together, but we're just going to save some time. I'm going to add these to our utilities class. You can create a new class for random number generation if you want to, but I'm going to put them in here just because I am lazy, and then add that as a member. So these are just, we create the random number generator in our utility space or in another class if you want to. So we don't have it in the engine anymore. And one thing I get here is, for example, these between methods, which are great for generating values between some extremes. So if I go back to DynamicEntity, we can check after we have updated our position. If our position is more than, do we have the game? Yes, we do. And we have world height. So if we've fallen out of the world, we can set our new Y position to something utils between and do, say, -4 to 0. So we spawn somewhere above the world or just at the edge of the world if we fall out of it. Go, go, go. So there we go. So yeah, we need to get some collision detection and collision reaction in place. And if you want to look at that, just a little call out here, you can go to SAT. Here's an article on collision detection with the axis aligned bounding boxes and the separating axis theorem. We've already done AABB. Here's links to some of the references that this stuff is built on. You can just copy this code into your base entity, and then we can start using it. Actually, I'm going to do that now. So we already have on collision, so I'm just going to grab is AABB and the separating axis theorem. And you'll notice this code is much, much simpler than the article it's built on because they take into account 3D and arbitrarily complex polygons. We only care about squares. But it's, in essence, let's see, I need to bring in a point, import that class. This is just a point that we can reuse. In essence, what this thing does is tell us how deep into each other two entities are colliding. Or rather, what is the shortest distance that we can separate them so they are no longer colliding, is what it will tell us. So first we will do the axis aligned bounding box test, and if that says we are colliding, we will call getOverlap to figure out how much we need to move to stop colliding. Hence, a very useful function. Just gonna check. I noticed that the HTML formatting broke the code a little bit, but this looks correct. So you can go grab that, and in the next video we will implement it and make sure that we can stay on the ground the way we want to do. See you then.